Fiber-optic Sensing Association, and welcome to our second June webinar, Grid Resilience Using Fiber-optic Networks for Understanding Underground Electric Grid in Congested Distribution Systems. And we have our member company LIOS presenting, which is a component of LUNA. We have Julio Toko and Yulia who will be presenting. We look forward to hearing your information. Julio?
Yes, thank you, Mark. Thank you very much for the introduction. As we're gonna go through this webinar, I would like to thank everyone that joined the call. We are very excited to talk about this project that was done a couple of years ago, and to also talk about the value that distributed temperature sensing for this project and acoustic sensing can do. A recap and go from there. I am doing the webinar with my colleague Yulia, who's our product manager. Myself, I've been with the company for quite a few years, 8 years now. So I look forward to continuously show the value of distributed fiber optic sensing and LIOS as a product.
All right, then let's get started with our agenda at first. Yeah, what we are going to cover today is just general information about the company LUNA, which we're now part of, what our company is specifically focusing on and strong at. We're going to speak about the products and which application areas we are covering. We will do then quick overview of what our customer case was about. We'll cover the background on the rating, and then Julia will continue with definition of the grid resilience, and we'll dive into the case study about RTTR. Next slide, please. Yeah, so let's start with introduction to LUNA. Well, we are the global leader in fiber optics. LUNA has its own technology, which is focusing on really being excellent and delivering resolution, accuracy, and speed with all of the devices in its portfolio. The spectrum of the customers really extends from military and defense, communication, automotive, energy, and aerospace. We are, I think what LUNA is quite good at is identification of the trends in the market and matching them with the demands in order to offer the best solution for particular customer application. And as a result of this, next slide, please. You could see, no, one more, thank you. Within the years of LUNA being in the market, which is since 1990, there were certain mergers in sales of the companies which were strengthening the focus of LUNA at really delivering the best technology and know-how transferred into devices. And since 2020, OptaSense has been acquired with now our dear colleagues, and now in 2022, LIOS is part of LUNA as well, which we're quite happy about, as we are really creating very strong synergies in terms of putting together devices for really turnkey solutions for a broad range of customers and applications. Next slide, please. Thank you. What you can see on the map is that LUNA is a very global company which covers offices really starting from the west to the east, and overall we have about 400 plus employees and have revenues about 87.5 million. And the company, of course, keeps growing and strengthening the bonds between different locations and chapters. Next slide, please. What is important to focus on is that for us to keep in mind the vision of LUNA, which is enabling the future with fiber. And I think many of us in this round already know about the very clear benefits of using fiber optics in sensing. And our mission is really to enhance safety, security, and connectivity of people by leveraging our expertise in fiber optic based technology and information that it provides. So as our CEO was saying, fiber optics is really the nerves of any kind of application and asset that can help you or help any kind of customer to identify the state of the monitored asset. And yeah, we're really trying to strive in improving our products to deliver the best solutions for the customers. Next slide, please. When we speak about LIOS, so the chapter of LUNA in which we are currently present, we can divide the spectrum of offers into 3 parts. One of them is, of course, the sensing solutions when we talk about the hardware, and that includes temperature, acoustic, and strain sensing. But on its own, that would be just a part of what customers would potentially need in order to solve their challenges. So what is very important in our portfolio is also our software platform that really provides a very good basis for integrating all of our hardware applications into one system and also integrating third-party devices in it. And on top, what one could do is really add plenty of analytical units and analytical engines that can give you real-time temperature reading for high voltage AC and DC. We can also do the estimations of depth of burial, not just estimations, but quite exact measurement. There is PD monitoring. We interact with SCADA, and one important for our customers factor is, of course, enhanced visualization that makes the customer interface very intuitive and simple. And of course, part of this entire system is our alarm management. Let's say that this works, but without really looking at every project, as all of you know, is very special and might have some underwater stones. So what we really try to do is really look into the real problems that lay in each case and not just copy paste solutions, but really adjust to demands of the customer. And of course, offer some training and monitor the state of the installation within the whole lifetime of it. Next slide, please. So what you can see here is the range of solutions that we offer from our portfolio. And you can see that there is a discrete and distributed line and also sensing on the long and short range. And with products from LIOS, OptaSense, and LUNA, we're really covering the short range and the long range application demands. And altogether, we are putting about 37 plus years of experience in distributed sensing, which is really a huge benefit in terms of really coming up with the best offers. Next slide, please. When we're looking at the range of the devices a bit more in depth, our DTS systems can can go up to 100 kilometers and have about 16 channels. We have two main technologies that we're using. It's Raman and Brilliant. The mean time before failure is over 45 years, which is an excellent situation for this kind of devices. And we have many certificates that ensure the quality and applicability of the devices for different setups. When we speak about distributed strain sensing, the extension of the length is about 70 kilometers. It's also offering 16 channels, and these are based mainly on Brilliant technology, OTDR, and we also can offer a SIL2 rating for those devices. For and dust measurements, distributed acoustic sensing, we are also, we can go up to 100 kilometers and offer a range of analytical tools together with the data and the actual raw data that comes out of it. And when we speak about products of LUNA, which is Odyssey and Hyperion, with Odyssey, one can get the high definition measurements and for strain, temperature, and shape sensing, which is basically above 1,500 sensor locations per meter. With Hyperion, long range discrete measurements of displacement, temperature, and strain, and vibration are also possible. So altogether, we're really covering demands for sensing on short range, long range, and in the matching of the devices in terms of strength, they really are put together like a puzzle. So it covers up the whole area of demands. Next slide, please. Julia? Thank you very much. So when we look at it all together, what we want everybody to keep in mind is that one part of our portfolio is not really not as not what we want to focus on. We really want to create an entire solution where hardware is providing the data to a certain software platform, which is currently Sharon, and we are working on improving our technology in terms of developing our software by integrating the software from LUNA and our own in order to make it more powerful and also flexible for the customers. And as output, you can get fiber optic temperature, you can get the hotspot detection alarm, thermal statics measurement, the real-time thermal rating, depth of burial, enhanced GPS maps, and various intrusion detection for cable, vessel anchoring, and manual digging. So this really covers up the entire spectrum of what could potentially go wrong with a cable and try to identify it in the right time and prevent it then. Next slide, please. At this point, I'd like to pass it over to Julio, who will speak more in detail about the case study of grid resiliency.
Yes, thank you, Yulia. I really appreciate your introduction. As you have mentioned, maybe going back to the previous slide, is that the whole point of fiber optic sensing has always been exciting to be able to monitor temperature, strain, and other variable, including chemical sensing also I've seen. pressure sensor, as we've done with the LUNA accelerometers. Today, we're really going to cover the idea of how do we go from using this presentation. We'll probably have a second part later on in the FOSA, hopefully later down the line. But the idea for this first part is how do we use the distributed fiber optic sensing instruments. The right instruments are always the one that provide the right data, properly calibrated, and to be able to provide solution. The solution that we're talking about right now are what's on the right. And for this particular talk, we are very excited to talk about the grid resiliency. What does that mean? What does it mean for previous project that we've done and for the project that I'm going to present today? When we talk about the resiliency, we talk today about climate change. We talk about other factors, including we talked even about third-party intrusion, anything that can affect the proper operation of the circuits, or whether secondary circuits or primary circuits. In this case, we will talk a little bit more about what the resiliency means. Is that when you design and operate a utility design the circuits and transmission line or distribution line, they have an understanding of what is the ampacity they need to have, what are the contingency plan on having multiple circuits, and what's very important is that to be able to operate those systems adequately, the resiliency simply means that they have to bounce back. They have to be able to respond quickly if one circuit is down, and to reduce downtime and be able to intervene at the right time, at the right moment, at the right location. That's why distributed fiber optic sensing also brings a lot of value there. And then to take actions. I would like to remind a little bit, one of the beauty about FOSA, we have quite a lot of webinar now as an industry. One of the webinar we did years ago for my company, at the time it was our sister company also, FIOPS, we work with IPL, and he presented. It's always great to have someone from the utility that present, because they are the users and they are our customers, and they have the vision about how operation should work. One of the good things about this project was really about asset monitoring. In that project, they talked about DTS and DAS. Today, we are part of the LUNA solutions, and it's very important to do a little recap of what was the value there and some of the words that came from that case study that we had done. From an asset point of view, in 2019, there was a FOSA webinar, as I mentioned, where we talked about pulling fiber optic in the duct bank to monitor steam lines that were affecting and damaging the medium voltage cables. What you could see also on the right, on the top right, was that this event where there was a few manhole explosions captured quite a lot of news and brought a lot of negative visibility to the utilities in Indianapolis. But what was great is that with the use of fiber optic cable sensing system using cables, they were able to monitor each one of those routes, be able to tell the steam company, utility operating the steam line, that there was an issue with the steam line that was leaking and affecting the circuit and the duct bank. What was very important about that case study was the fact that it was asset monitoring. The asset monitoring was to focus on catching when the steam line is affecting the duct bank, affecting the power cables, and reducing the lifetime of the power cable by losing the duct bank because it gets destroyed with the highest temperature, and by losing the power cables, the circuits, they have to reinstall the circuit. It takes a long time. One thing that they mentioned in that presentation was that at the end, on the left, there is something that called rating and how you can derate a circuit simply because there's a steam line. In that FOSA webinar, what was brought in, the first thing was explaining that these cables, the contingency plan, part of the resiliency built was to be able to push 294 amps in those circuit, medium voltage distribution line. However, by seeing the steam line, it's affecting the entire duct bank. And what they show over here is the ability to do enough line calculation and understand what is the rating of the cable if it was next to the steam line. So in the case of them, IPL, as a utility, by doing a quick calculation on SIMCAP offline, which SIMCAP is the software that many utilities have been using to do some design. And I'll cover a little bit more on that, is that for us, it's important to understand that you also are derating your line. So instead of being able to push 294 amp, they only push 252 amp. Okay, so one of the biggest problem is like it can be misleading to operators who are trying to operate the line and understand that they can still push 294 amps. In reality, they cannot. One of the advantages of the same fiber optic that was installed, they also showed that they can do cable fault location and fault detection as well. What was presented at the time, what we hope to do in the next webinar is to show how you can also use DAS for, I will not say partial discharge monitoring, because that is not true. There is certain things you can do, but detecting different anomalies in joints. So, but one of the advantages is that to remind that in this case, years ago, it was about asset monitoring. Today, what I would like to present really is about how can we make sure that the operator can do this analysis real time. Instead of doing analysis using a MATLAB, a SIMCAP, what we are presenting today is a different project with a similar challenge where the operator and the utility was able to monitor real time and also offline the RTTR values, the rating of the cable and of the circuit. Just a brief background, because I'm pretty sure a lot of people are familiar with this, but the idea is that you have different power cables. You have dielectric power cable, you have oil field power cable as well. What we care more about is the dielectric power cable. We have the medium voltage, high voltage, up to 500 kV. And the limitation of these cables are always whether or not they can sustain the temperature during operation. So every time you have ampacity or electricity flowing through the conductor of the cable overheats, and the limitation is the insulation or the dielectric. For XLPE cables on 90 degrees Celsius, for continuous operation, EPR 110, both can go higher for emergency, and we can talk about that later. The installation over the years have always been high voltage cable can be embedded, fiber optic, or it can be outside. And for distribution line, it can be in a duct bank in adjacent conduit next to the distribution network. What that simply means is that what is RTTR, or we call real-time thermal rating, is that if you have a maximum current passing through the conductor, you are limited by the temperature of that of the dielectric that's used to build the power cable. In this case, what it simply means is the temperature is increasing, you're losing your ampacity rating. So in the steam line situation that was presented earlier, that was the case. Every time there is a steam line, the temperature goes up. You're affecting the duct bank, you're affecting all your circuits, and strategically, even the circuits that are closer to the steam line. We'll talk a little bit about LIOS RTTR, what makes us special, what makes us separate and different from others. One of the main features really is that it's the FEM, finite element modeling approach. But what we could do with that now is that for special project, challenging project where you have a congested duct bank as represented, and then we'll see, you can use the fiber optic that's embedded in the power cable, or you could also use the fiber optic that's away from the power cable in an adjacent conduit. And you can also go further out, about half a meter, with guaranteeing an accuracy, as we showed here, of 0.5 degrees Celsius, plus or minus 1 degree Celsius, and up to 0.5 meter. Okay, so this is very, very important, because the main point here is the accuracy of the DTS measurement. So good instrument. The second thing is, what you really need is a strong engine that can be able to look at and leverage the fiber optic technology by looking at the temperature of no longer the fiber temperature, but the ability to start looking at the conductor temperature for each one of those circuits. And from a quick illustration point of view, is on the left graph, you will see the necessarily you see technically how operators operate the circuits. They can go at 600 amp, then they keep going up and down based on the load and the demand. Peak hours between 8 a.m. and 5 p.m. and coming down also. And these transients that are happening on a daily basis, especially for distribution network, correspond to what we see on the right here. You'll see that in red is the fiber temperature responding to the current or the load onto the line of the circuit. And then you see in blue is your conductor temperature. And the conductor temperature means that if the fiber optic was away from the power cable, is at, I give an example, 40 degrees Celsius, in reality, your conductor is already at 80 and your limit is at 90 degrees Celsius. So it's very, very important to know that we have the capability to have that. So that helps operator understand how they can really dynamically look at these lines and operate the lines. At the same time, we do a COMSOL analysis to prove our algorithm and to look at our accuracy. So looking at this retrofit project was similar. Fiber optic sensing pulled already existing telecom lines already existing from a substation, going to different routes and different substations. In this case, with the RTTR platform LIOS, what we have is automatically where the DTS was installed at the substation, you have different route where the DTS goes, and we can see the crossings of where the hot steam lines are below the duct banks. And these are strategically located. The client has nothing, he cannot control necessarily the steam lines because this belongs to another utility. This is not the same project, but this is a different project. But what was very important here is that you can see the different routes. Using the telecom fiber, you can actually understand how first the duct bank configuration, the duct bank is looking thermally first. What gets more excited is that we can take that duct bank information, we can get the drawings from the customer, pull that in our system. Our engineer can do the final element modeling for the RTTR for us, compare it to COMSOL and come back with a model and be able to insert that in our software so that we can have a real-time thermal rating, live data running with the current value from the operator, at the same time predicting how long they can run the circuit before damaging it. Essentially what we are interested in before there is any steam pipe or not, congested duct bank looks like this. Normally you have multiple circuits, fiber can be here. It's extremely challenging, but the exciting thing is that as the temperature is increasing, your fiber is also seeing the temperature, and then you can be able to interpret and extrapolate because we are modeling each thermal, let's say layers between the fiber and each of the circuits. We'll be able to know what is the temperature of the system. Not only the fiber optic temperature, but most importantly, each circuit will be able to be detected. One other thing is that based on that, we give you an accuracy, how well the circuit will work, an accuracy plus or minus 0.5, depending on how far you are from your cable. Another case, which is exactly the case for this time, you have the duct bank that is heating the same way, but at the same time, you also have a steam pipe that's affecting you and then heating this particular circuit. So in reality, when you think this circuit is seeing, let's say 30 degrees Celsius, the steam line is affecting it, and also the other surrounding circuits are affecting the duct bank, including the circuit. So these are very, very challenging system and algorithm to be able to implement. But the beauty about the LIOS RTTR that we have, it's a self-learning algorithm. As you can see, it can catch up, including when there is a heated external source that shows up. In this case, you can be operating your line, different transient temperature is going up and down, and then the heat source is turned on. You can see the system will still be able to catch up, and it takes about 9 days after the original installation to be able to catch up and understand. So it's a self-learning algorithm, and it keeps seeing all the environment and keeps learning about the environment. When we did the initial connection, we can see already the hotspots showing up. These are the 3 crossings that we showed on the map. automatically you can see between 60 and 65 degrees Celsius is the fiber temperature. This is already a red flag because that simply means that your conductor temperature are probably at higher temperature. As you can see, the three ones hotspot, the red one is the hottest, operating around 70. This temperature is not changing that much, but you can see that the blue one is also changing based on season a little bit. So the circuit of interest or the circuit surrounding or crossing the steam, where the steam line is crossing, and that's what we're going to do the analysis of. This analysis is really to highlight the value of the RTTR. What we do is first we look at the temperature that's in blue of the fiber, and then with the information that we implemented into the system, we can now extract the conductor temperature of the circuit. So the circuit that's closer to the steam line, we could automatically see as they're operating the circuit. If you zoom in this section, it's already at 115 degrees Celsius. Sorry if it's probably small to see the writings, but we are already at 115 degrees Celsius. What I would like to emphasize is that in cyan is the fiber temperature, in red is the conductor temperature, and in green is what the operators are actually doing to the line. They're actually transmitting or distributing some loads, and you can see how daily it changes. So peak hours coming down and the conductor temperature goes up. It is clear that you can around 100 and 250 amp automatically. Every time the load goes above 250 amp, this triggers a conductor temperature about 115 degrees Celsius. This is way beyond the 90 degrees Celsius limit. So from a resiliency point of view, the client should be able to know that they cannot keep operating it, even though the duct bank temperature seems fine. Without fiber, they will have never known that they're actually operating much higher load than the cable was rated for. A quick zoom in to look at this data. As mentioned, we are looking at 90 degrees Celsius. Every time they go up to 220, 250 amp, automatically they trigger that. So what's now important is that these operating during distribution, they sometimes have emergency situations where they need to use the line anyway, because they need to reroute the line, the load from one circuit to another. Another circuit might be in maintenance, so this line has to be used. How do we take this information to help operator? That's where things get very, very exciting for this application. In this case, what we do is we ended up looking a little bit in terms of time. You have 3.5 hours. By the time they turn on, they demand more load. There's about 3.5 hours when they are running it. That's how long it takes to operate the circuits for their loads, but they see 115 degrees Celsius. Here's a 6 hour, 4 hours, and another 4 hours and 12 hours. Different days of the year, different dates, 300 amp, what's going on with the circuit. They are all exceeding 90 degrees Celsius as we discussed, but what gets very exciting now for the operator is that they can say, I can still push a few more. If I look at, and I'll try to explain this graph. This is the time, number of days in July, and this is the cable rating, capacity rating on the cable. And on the right is the conductor temperature. So what that simply means is your conductor temperature here, we want to make sure that it stays below 90. And for that to happen, the operators have to realize that they have to keep operating the line at mostly below 250 amp. And I will show that quickly in the next iteration. The slide. 90 degrees Celsius is the limit. At the same time, 250 amp. So when they're operating, they can see that I can never operate this line for more than 2 hours. After 2 hours, I'm losing it. I'm losing my rating all the way to 0, 10 amp. I can only push 10 amp. And they can see that every time they are overloading the line. What gets very, very interesting as well is that at the end, what they have is this screen out of the software that they can bring in the dashboard, and to see that for the next 2 hours, they can push 239 amps. So if somebody calls them and asks them that they have a bigger load of about 220 amp, they say, yes, I can give you 239 amp for 2 hours. And I can give you 226 amp or 220 amps up to 8 hours. After that, I cannot go any more beyond. And if they keep going higher and higher, this is the information that they're getting from the dashboard to tell them that they cannot push any ampacity. They already reached 112 degrees Celsius as a conductor. So now this changes the operation quite a lot. If you have a secondary or primary circuits where you have a dedicated line, let's say an example, a data center or a manufacturing plant, and those guys have peak hours where they need to produce more over time, you can tell them that I'm giving you 239 amp or 1000 amp for 1 hour, 2 hours without damaging my line. So that's another thing also when you talk about resiliency, is the ability to know exactly where the bottlenecks are, what is the contingency plan. After the 2 hours, they can switch to a different circuit. And this is really what the value that we get excited about the RTTR and the capability of the distributed temperature sensing system, including the LIOS RTTR. So from a summary point of view, very simply, how do we go from asset monitoring, as we presented in the previous webinar, to today helping operators make decisions real time? And to keep that information also to know that, for instance, this summer in Los Angeles was quite catastrophic. We're gonna be preparing next summer. We can pull that data back. Next time we have 120 degrees Celsius. I'm exaggerating in the duct bank, and probably because at the end of the day, there is a steam line, or there is also a high demand due to the summer is a hot day of 40 degrees Celsius or 100 degrees Fahrenheit in the city, and everybody's got the AC on. So this can properly be achieved with DTS mostly. And as we show cable fault, and we're going to show more on the joint monitoring in next webinars. What's also very excited is that from an asset point of view, it's very simple, but to turn into operation, operators are very, very excited because that data sits in the database, the PI, and they can actually turn the knob up or down every time the demand is there. So this will be the end of my presentation of our webinar, at least before we get to questions. But before we get to that point, I would like to say that really give a special thanks. The LIOS family would like to give a special thanks to Willem Hill. Dr. Willem Hill has been with the organization for 15 years. He's been a great contributor to the organization and to FOSA. All of this vision that we've been talking about, you go from instrument to be able to implement dynamic rating to help operators, engineers, utilities, including other operators for oil and gas, has been fantastic. The ability to have a good platform, as Sharon we've been discussing, the dynamic rating has been fantastic. The depth of burial, those are the vision that he helped lead in the organization, and many more contributions that he's done with more than 23 patents. Willem is retiring next week, so he's going to be highly missed. Hopefully we can keep him in the family and keep working with us and not go too far, because there are quite a lot of exciting things in bringing value and solutions to our customers. I would like to also say thank you to Dr. Sudhakar Cherukupalli. Carl Maid is the owner of the project, Dexter Tarampi. Martin Ucheski as our engineer was really the brain behind RTTR and dynamic ratings, and also Max Bohana, who was able to execute the project for the organization. And thank you, Yulia, and the floor is for everyone.
Well, thank you very much for a very informative presentation. And let me just echo what you had to say about Wieland. Obviously, you're mentioned his contributions to FOSA. They were really extraordinary, and our technology committee that he was an active participant was in very much benefited from his leadership and from his active participation when he was a regular member of it. So let me agree with you there. To ask a question, you can type it in the box, which on your webinar is to the right. But Julia, rather, I wanted to kind of give you an opportunity to expand on how the economics of including fiber optic sensing enhances the utility transmission. As I understand it from your presentation, it allows utilities to more precisely identify the maximum load and the period of time. how does that translate into enhanced productivity and obviously sounder economics for those utilities?
Yeah, very good question. What it really does from a economic point of view is one, if we look at just the asset monitoring, the civil work that goes underground infrastructure is costing. So when we talk about the resiliency, is that if you damage that infrastructure or you don't understand how it's operating or the limitation of it, it costs you easily, when you talk about distribution line or transmission line, even higher in terms of cost, is costing you millions of dollars. The second thing is, now, if each one of those lines goes down because you're overriding it without knowing that you are destroying the circuits or the cables, you're also losing a lot of money because the downtime cost. What's happening with electricity is it's being traded as well. So when we talk about dedicated line, as I was explaining, the fact that you can push a little bit more for 2-3 hours is extra amount of dollars per minute, per hour, kilowatts per hour that you keep doing, you keep generating for the organization and for the let's say the community in a different way as well. So we talk about productivity, is that a data center, for instance, a manufacturing plant. So in terms of efficiency, installing fiber optic, it's first of all just simple to understand assets is fantastic, but to be able to now tweak it by using the RTTR, like the LIOS product that we have, you generate extra money every kilowatt hours that you're delivering. Yes.
Thank you. So the next question is really, you referenced that there were sort of a number of scenarios in terms of the availability of fiber. Could you kind of elaborate on that? Do you normally encounter that usable fiber is already in place, or is it necessary? So how often is it necessary to add additional fiber or to install additional fiber in order to activate sensing?
Yeah, so in this case, for this particular project presented, the fiber optic was already there for telecom. So in those situations, we need to understand which kind of fiber optic it is it single mode or multi-mode? And then the advantages within our line of product, we can have either a DTS that's single mode or multi-mode. So we can use standard fiber optic cable, pull one strand, and if in an adjacent duct bank. What's quite important is to still do the calibration. What's not showed in this presentation, because I wanted to focus on the high value, is that the calibration was properly done to make sure that if you're reading 70 degrees Celsius on DTS, it's truly 70, it's not plus or minus 20 degrees, because that's going to affect your RTTR. This is why a good DTS is very important for this application. But the fiber, most of the time out there for telecom, this is why retrofitting is a perfect application for that. Distribution channels of the network are very dynamic. So that's one advantage.
So this next question is effectively a follow-up. If the fiber is offset from the conductor, is the fact that the thermal diffusivity is unknown an issue?
Yes, so if the fiber is away, we take the duct bank configuration. We actually look at the cement information and the geometry of the duct bank. One of the advantages that then we start seeing in our RTTR or the simulation is, if it takes the power cable is overheating now, and it's probably going to take 2 hours, 3 hours before you see the latency of the fiber optic cable, then we account for that. But what's very important is that those are just, let's say, models that we build. But as soon as, one of the advantages of the RTTR that we have, as soon as you install it, the system is self-learning to understand that I'm actually seeing another heat source, or I'm actually cooling faster or better, the resistivity of the soil is better. So all of that is, you start with a model, and then that model is self-adjusting in the field. That's really what makes it exciting. So you start with the understanding as the diffusion of the heat, propagation of the heat radially, but at the end of the day, what happens, what's very important is the fiber optic itself and the instrument are self-learning, and the algorithm self-learns about the resistivity of the system. An example of that means, if that season it was cold season or winter, that diffusion would be different, because the resistivity of the environment has slightly changed for a duct bank that could be flooded, for instance. So that's the advantage of the RTTR. It keeps learning about
that. So following up on that, you mentioned in the RTTR method being validated by simulation. Did you also do sort of verification with actual deployment, or what's the balance between the simulation and actual deployments in coming up with your information?
Yeah, that's another good question. What we have done is that we do the simulation of using COMS or final element modeling after we build our model to validate it. And then we put in the field and we see it. We have done quite a lot of case studies where we have used either thermocouple, we have done dummy loop where we drilled into the conductor and put on the jacket of the conductor to see also if we are matching it. And the results have been very, very fantastic. We've been within plus or minus 2 degrees Celsius. So this is really important to say that this type of algorithm are great when you compare the simulation, but the real world is there. And this real world is dependent on different factors, as I mentioned, weathering, soil being removed and put different type of soil. It adjusts, and we have proven that the algorithm works in the real world as well by comparing to empirical data. Yeah.
So one of the really exciting things you've talked about is the improvement in the software, the ability of your algorithm to how shall I say, have enhanced precision. Could you elaborate as to over time, sort of the rate of improvement that software for sensing has gotten better?
Yeah, I think right now we have it's constant improvement. First has been the speed of the system. I say at the beginning, for instance, what we needed is also a reference temperature. Over the years, a reference temperature means that if you have a fiber optic next to a power cable or embedded to the power cable, you have to have another fiber optic on the soil away from the power cable as a reference to see what the temperature of the soil. That's how we started years ago. And then after that, we have improved the algorithm so well that we don't need the reference anymore. So if you think about it from a cost point of view and elegance of installation, you don't need to run 2 fiber optic. If you already have 1, you'll be fine. And then we improve the speed, we improve the reliability of the result. We kept improving also situation where you have multiple thermal models and understanding the bottlenecks, which bottlenecks are the ones that should not be the one to pay attention to and which one are the ones. So really the speed and the accuracy of the algorithm is what gotten much, much better, especially for the distribution network that we just showed. Those are very complex and hard. Not many people can do this kind of analysis simply because it's extremely dynamic and it's very complex, especially with the fiber not embedded in power cable.
Thank you. Would you comment a little about as countries around the world are upgrading their electric grids, are there some areas or countries that are doing more in terms of adding advanced technologies like fiber optic sensing than others?
Yes, we've seen some very interesting markets. It's almost like the greener markets, the ones that are new and putting this new infrastructure, already have the mindset of putting fiber optic. So an example, you see more and more in Asia, you see more and more in Latin America. Europe has been extremely advanced in putting fiber optic sensing. As a matter of fact, it's tied into quite a lot of different things, including insurance, but monitoring has been important in Europe and it's trickled down in other countries. America is also picking up quite strongly, but I would say right now is where the infrastructure a little bit greener, where they're starting from scratch. It's perfect because they are easily adopting it. Yeah.
That certainly suggests that greenfield or sort of new installations is better. So does that better in the sense of is easier in order to get early adoption or get appropriate adoption? Then are you seeing the use of renewals driving more of more use cases?
Yes, renewables for sure driving a lot more cases, especially offshore wind farms, also onshore wind farms. What we're seeing is when you have direct burial where you don't use duct bank, it's quite quite important to be able to understand where your cable, if you're using native soil. However, when we come to the situation of why I wanted to present this project is that even the brownfield, for a distribution point of view, back in the days, it used to be always high voltage. There's a lot of potential in distribution networks because it's easy to pull a fiber on an existing brownfield, or they already have a telecom fiber. And the dynamics of it are much more than the transmission line that are high voltage compared to, let's say, the medium voltage. I would say it really depends on educating the operators and the user and the utilities out there.
That's good, very helpful. So if you've again, going back to the comment about the different types of fiber that you can work with, if you could pick in advance which fiber would be already in place, what would be your preference?
For power cable, I would say we don't have a preference really. Single mode for us has never been a problem to make a single mode system. For telecom, mostly single mode. Multi-mode gives you better resolution especially for certain ranges. I would say up to maybe 20 kilometers, you get good data with multi-mode, but you have to understand also there's a compromise between the type of fiber and the number of connection and splices that are going to be there. So I almost treat it case by case, and whatever is simpler for the end user, what's already there will accommodate and we make it work. Yeah.
Well, clearly that flexibility will be very encouraging for prospective customers. Sort of next question that we generally get is just a reminder that this particular presentation will be available along with all of FOSA, Fiber Optic Sensing Association's other presentations on our YouTube channel. And I appreciate the fact that you referenced some of the related webinars that we have done in the past, and certainly they're available to reference as well to find out a little bit about how sensing works for electric transmission. We do not have any more questions, so Yulia and Julio, thank you very much for a very informative presentation. This concludes the webinar.
Thank you, everyone. Thank you, Mark, and thank you, Joy.
Thank you, everybody.